I remember as a kid playing with a game or toy called Spirograph. I suppose I played with it as an adult too. It used to come with these gears that look kind of like this. Um, and you would take one gear, usually a bigger one, but it could be a small one, but you'd take one and you'd pin it to your paper. So you'd have, cardboard in the back or something. You'd fix it to the paper. And then you'd take another one and you'd just put it right up against it so that the gears were meshed in. And then this one would have holes in it. You could stick your pencil in one of the holes and then you just roll around, and your pencil would go in and out as you were trying to roll around. You try not to slip, and you'd end up with these just crazy looking great things here. It goes like this here, that I'm going to watch this point right here as it rolls around, and it'll generate that curve, right? This is what you would do with your pencil. And depending on the relationship between the two radii, you'd get different curves. I mean, this one is, the fixed radius is 30 and the rolling radius is 10, so there's just a 3 to 1. But if it was a little bit different relationship, then you might get something a little different here, right? And there are all kinds of crazy things that you could draw. That gets to be really, really complicated. But the idea is the same. It's just a matter of what's the relationship between the gears. How many teeth does the fixed one have? How many does the rolling have? I want to do one example of this. And I want to do the one we started with here with just 10 right there. Now this has it drawn starting over here, but we're going to start it up on top so it looks a lot like the cycloid calculation that we did in the last video. So off to calculate. Okay, so I've got my big one, which will be the radius 30, and then I've got this little one, which will be my radius 10 one. I'm going to stick it right on the top, and I'm going to follow what happens to this point right here as it rolls around. Okay, so that circle, let me, no, don't erase it. I want to copy it and paste it. All right, that circle, I'm going to roll it just a little bit here so that the point of contact is now down here. The red point will have moved up a little bit. Okay, so let's see. I'm going to draw a line connecting the centers here. That was a little bit long, but I'm going to draw a line connecting the centers there. So this is 30 to here and 10 more to there. Likewise here, 30 and 10. Those are the two radii of the circle. The thing that I know is that there's no slipping. So the arc that got turned through here is the same as the arc that gets turned through there. Now the radii of the circle are different, so this angle here, when I draw this thing in right there, this angle here will not be the same as that one. I'm going to let this one be the one I use as my parameter. Well, let's call it theta for now. Okay, and let's call this angle up here alpha. Now it turns out that they're very closely related because those arc lengths are the same. Well, from the point of view of the big circle, that arc length is equal to the radius times the angle. On the little circle, it's also equal to the radius times the angle, which lets me see that that angle alpha is going to be 3 times whatever angle theta is, right? So whatever angle you have here, this is going to be 3 times as much. Well, the ratio is 3 to 1. Now, what I need to do is I need to find the coordinates of this point at any point in time. My coordinate system is going to be drawn so that my x-axis is here and my y-axis is, vertical this way, right? So my fixed circle has its center at the origin. Okay. Notice that the center of the rolling circle is actually just going to stay on a circle of radius 40 all the way around, and that this point here is going to be going around that point as it moves around. But let's see what we can do with this. I need to find the coordinates of this point. Actually, What is easy for me to do is to find the coordinates of the center, because as I just said, it's on a circle of radius 40 and you've turned through an angle of theta. So I look at this thing and I say, well, let's just grab the x coordinate and the y coordinate of this point, right? The x coordinate is going to be, drop a perpendicular down here. Well, actually, I've already got that there. The x coordinate is that length right there, which is the sine of that angle times the hypotenuse. So that's 40 times the sine of theta. Right? I dropped to the y-axis, so my x coordinate is the opposite side now. Right? Likewise, because I dropped to the y-axis, my y coordinate is going to be the adjacent side. So the y is going to be 40 times the cosine of theta. Right? So if I turn through that angle of theta, then I know the coordinates of the center of that rolling circle. Okay. Now I'm going to adjust those by a little bit. I'm going to zoom in here, and I'm going to say whatever this x coordinate was, I've got to subtract something off in order to get to this one. Well, how much do I have to subtract off? I have to subtract off, I'm going to do this in purple. I need to subtract off this much, right? For the y coordinate, I need to subtract off this much. Well, there's a right triangle in there, if only I knew what that angle was. Well, what I want to do is actually think about dropping a perpendicular this way. Right. If this were the cycloid problem, then the amount of rotation that this has gone through would be just whatever alpha is. But see, there's a little bit different picture here because the ground is actually turning. So this circle, as it rolls, has both its own rotation and the fact that the ground is rotating away from it. And so the angle, the total angle that this is rotated through now is this angle theta. This angle right here is theta. That 10 is in my way. I'm going to see if I can get rid of it. Right. This angle theta is the same as that angle theta down there. So the total rotation here is actually theta plus alpha. Right? And maybe it's easier to see rather than drawing that triangle there. Let's draw that purple triangle here. Drop it this way. Because there's the angle theta plus alpha. There's the adjacent side to it. There's the opposite side to it. And my hypotenuse in there is 10. Okay? So zooming out a little bit here. This little bit here is going to be 10 times the cosine of theta plus alpha. And this side in here is 10 times the sine of theta plus alpha. Right? Now remember, alpha is equal to 3 theta. So the theta plus alpha here is just 4 theta. Likewise here, this is just 4 theta. So, coming down to here, where am I? I think we've got it now. That the x-coordinate of this red point is the x-coordinate of this center minus that much. So I've got to subtract off that 10 sine of 4 theta. Likewise, the y-coordinate is going to be this thing minus that much right there. So that's minus 10 times the cosine of 4 theta. So there's what I think my parametric equations look like. One of the things I want to point out here before we swap over to the computer and double check this is that this bit right here is describing the path of the center of the rolling circle. It's a circle, right? So the center of that rolling circle is moving along a circle, and then there's this stuff over here. That this stuff over here, including the minus signs, is describing circular motion around that center, right? This is if this center was staying still, these were just constants, then I'd be describing that constant plus a sine curve, this constant plus a cosine curve. That would be describing a circle with that center. Okay, but that center is changing. So this right here is rotation around the center. And one of the things that we've had to do carefully is to figure out that this is a 4 theta here, that because the relationship of these things was 3 to 1, somehow this turned into a 4. And the theta plus 3 theta was 4 theta. So let's swap over to the computer and see if those equations actually do give me the curve I think they do. So here we go. Okay, I'm back in my graphing calculator. I've got the parametric curves version. I'm going to look at the black curve. I'm going to plot this from 0 to 2 pi. Just go around once. And the formulas that we just calculated were 40 times the sine of t minus 10 times the sine of 4t. And then for the y value, we had 40 times the cosine of, so I got times the cosine of t minus 10 times the sine of 4t. And let's see how that does. Oh, I don't see anything because I'm zoomed in too far. Let's go out here, and this is not giving me what I thought. Oh, because I didn't type it in right. This was a cosine. So I had sine. Let's try that again. Ah, that looks better. Yeah, notice I started up here at the top, and it does 1, 2, 3 loops. It's like a cardioid, but it's on the outside of a circle. I believe this is an epicycloid. Maybe it's a hypocycloid. I can never remember. It's either an epicycloid or a hypocycloid. I should probably find out. After some quick and extensive research, it is an epicycloid on the outside. If the circle had been rolling around the inside, it would be a hypocycloid. Anyway, do some playing, do some experimenting. It's fun stuff. See if you can do some others. Have fun.